To understand the Earth's dynamic surface, one must first dive into the concept of plate boundaries. The Earth's outer shell, known as the lithosphere, is not a single, unbroken layer. Instead, it is fragmented into massive slabs called tectonic plates that float atop the semi-fluid asthenosphere beneath. These plates, ever so slowly, shift and interact with one another. The edges where these tectonic plates meet are what we call plate boundaries, and they are the crux of the planet's geological activity. Plate boundaries are the scenes of some of Earth's most dramatic and transformative processes. From the towering peaks of mountain ranges to the fiery eruptions of volcanoes. From the yawning depths of oceanic trenches to the trembling power of earthquakes, the interactions at plate boundaries shape our planet in profound ways. But to fully appreciate their significance, we need to explore the fundamental forces and phenomena at play. These plate boundaries are not mere lines drawn on a map. They represent zones of intense activity where plates collide, pull apart, or slide past one another. The movement of these plates is driven by the heat from Earth's interior. Deep within the mantle, convection currents, caused by the slow churning of molten rock, push and pull the plates in various directions. It's a slow dance, with plates moving only a few centimeters per year. But over millions of years, these movements leave an indelible mark on the planet. When plates interact, their boundaries can be categorized into three main types: divergent, convergent, and transform boundaries. Each type is associated with unique geological features and processes, and together they tell the story of Earth's restless crust. Divergent boundaries are zones where plates move apart. These are the birthplaces of new crust, where molten rock rises from the mantle to fill the gap left by separating plates. Most divergent boundaries are found along mid-ocean ridges, such as the Mid-Atlantic Ridge, where underwater volcanic activity continuously creates new oceanic crust. If you were to travel along the ocean floor, you would find a sprawling network of these ridges, forming the planet's longest mountain chain. On land, divergent boundaries can form rift valleys, such as the Great Rift Valley in East Africa, where the crust stretches and thins, giving rise to deep fissures and a landscape in transition. Convergent boundaries, in contrast, are sites of collision. When two plates meet, one is often forced beneath the other in a process known as subduction. This type of boundary is responsible for some of the most dramatic topographical features on Earth. The collision of two continental plates, for instance, has given rise to the Himalayas, the world's tallest mountain range, where the Indian plate continues to push against the Eurasian plate. Meanwhile, when an oceanic plate is subducted beneath a continental plate, it creates a trench in the ocean and volcanic activity on land, as seen along the Pacific Ring of Fire. The Andes Mountains of South America and the Mariana Trench in the western Pacific Ocean are prime examples of this process. At transform boundaries, plates slide past one another horizontally. These boundaries are marked by strike-slip faults, where the motion is largely lateral rather than vertical. The most famous of these is the San Andreas Fault in California, a tectonic boundary between the Pacific Plate and the North American Plate. Transform boundaries are hotspots for earthquakes, as the plates become locked due to friction and then release energy when they suddenly slip. Beyond these primary types, there are also complex plate boundary zones, where interactions are not easily categorized. These regions, often found in areas with fragmented plate edges or overlapping movements, add to the complexity of Earth's tectonic system. But what makes plate boundaries so remarkable is their ability to create and destroy. At divergent boundaries, new crust is formed, adding to the size of plates. At convergent boundaries, old crust is recycled into the mantle, ensuring that the Earth's surface area remains constant over time. This balance between creation and destruction is a testament to the planet's dynamic equilibrium. The processes at plate boundaries are not isolated events. They are interconnected, with one action triggering another in a cycle that spans millions of years. For instance, the subduction of an oceanic plate beneath a continental plate can lead to the formation of volcanic arcs and mountain ranges. The movement of plates at divergent boundaries can influence ocean currents and, consequently, global climate patterns. Even the slow grind at transform boundaries can have far-reaching effects. As earthquakes reshape landscapes and impact human societies, plate boundaries are also a window into Earth's deep history. By studying the patterns of plate movement, geologists have pieced together the story of supercontinents like Pangaea, which existed hundreds of millions of years ago before breaking apart to form the continents we recognize today. Fossil records, too, reveal how plate movements have influenced the distribution of species, creating isolated ecosystems and driving evolutionary processes. As fascinating as the science is, plate boundaries are also a reminder of nature's raw power. The earthquakes and volcanic eruptions associated with these zones are stark reminders of the planet's dynamism and unpredictability. These events, while devastating, are also crucial for understanding the mechanisms at play beneath our feet. Scientists study seismic activity, volcanic eruptions, and the movement of tectonic plates to better predict and mitigate the effects of these natural disasters. Humanity's relationship with plate boundaries is a complex one. While these zones are often hazardous, they also offer resources and opportunities. Volcanic soils, for example, are incredibly fertile, supporting agriculture in regions like Java in Indonesia and the slopes of Mount Etna in Italy. Subduction zones and rift valleys are rich in minerals and geothermal energy, providing economic benefits to communities. However, living near plate boundaries requires resilience and preparation, as the risks of earthquakes, tsunamis, and eruptions are ever present. In recent years, technology has advanced our ability to monitor and study plate boundaries. Satellites equipped with GPS track the subtle movements of plates, while seismographs record the tremors that reveal the inner workings of the Earth. These tools not only enhance our understanding of tectonic processes but also improve early warning systems, potentially saving lives in vulnerable areas. The study of plate boundaries is a journey into the heart of Earth's geology. It is a story of immense forces operating over vast timescales, shaping the landscapes we see today and paving the way for the Earth of tomorrow. From the depths of oceanic trenches to the heights of mountain peaks, from the quiet spreading of ridges to the violent shifts of earthquakes, plate boundaries are where the Earth's story unfolds in real time. They are a testament to the planet's ever-changing nature, a reminder that what we see today is just one chapter in a geological narrative that spans billions of years. As we continue to explore and understand plate boundaries, we gain not only knowledge of our planet's past but also insights into its future, a future shaped by the same forces that have been at work since the Earth's formation.